Okay, my name is Dick van Kampen and I'm affiliated with the Eindhoven University of Technology in the Netherlands. It's a pleasure and honor for me to welcome you all to this invited lecture by Professor Jacques Huyghe, which I will be sharing. First, let me shortly introduce Jacques Huyghe to you. Jacques holds the Bernal Chair in Biomedical Engineering at the University of Limerick in Ireland. He combines this with a secondary appointment at the Eindhoven University of Technology in the Netherlands. Jacques is well known for world-class research in poromechanical modeling, with particular reference to swelling, fracture, and large deformations. Over many years, he repeatedly advertised the close analogies between biological tissues and geomaterials and the urgent need to exploit those analogies in developing numerical models and clinical and industrial technologies. Within his research, Jacques has the unique ability to carry out and integrate numerical, analytical, and experimental work on the highest possible level. In view of his achievements and reputation, Jacques has been recently bestowed with the InterPore Kimberly-Clark Distinguished Lecturer Award. As a recipient of this award, Jacques will be giving his current invited lecture, which is entitled Poromechanics in Extremely Large Deformation, Swelling and Fracture. Now I invite Jacques to present his lecture. I will put off.
Thank you very much, Professor Van Kampen. I will move to sharing my screen. Okay, I hope everybody can see.
Yes.
First of all, I would like to thank once more the committee for the Kimberly-Clark Distinguished Lecturer Award to offer me the opportunity to have this award and to move around the world to present this work to companies and to academia. Today, I will talk about poromechanics in extremely large deformations. And my co-authors are very many, so I don't specify them here on the first first slide, but I will come back to this as I come to the end of this presentation. So since 5 years, I am Bernal Chair of Biomedical Engineering, and Bernal Institute is a project of about €100,000 in the west of Ireland, a place where there is more concentration of biomedical companies than anywhere in Europe. And the applications we think about within Bernal Institute range from advanced computational modeling, aeronautics, material science, microscopy, pharmaceutical science, molecular biology, and energy technology. The specifics of what I'm going to report about is work done together with Procter & Gamble on diapers. What is shown here on the video is one small particle, typically dimension of a few hundred microns inside the diaper that you see on the baby on the right. and this small particle swells as soon as it comes into contact with a gush of fluid. Now, in order to slow down the swelling and allow the fluid to reach deeper layers in the diaper, a cross-linked layer is applied to the particle and cracks as swelling goes on. So we have to do with swelling and with cracking. But there are many, many other applications which we can think of to apply this technology of simulation of fracture and swelling. So we'll have these two themes in our presentation, and to give a little bit a context in which I'm presenting this work, I've been plotting the different porous media which have been discussed in this conference until now. And I plotted them on a 2D picture showing vertically swelling propensity and horizontally deformability. And the deformability of the porous media goes across a range of many orders of magnitude, where we start on the left side with the stiffest ones, bone and sandstone, going down to the most deformable ones, which are living cells and superabsorbents. And what we are particularly interested in is the right upper corner of this graph, showing the most deformable and most osmotically active media, which are generally known to be the most difficult to describe. So to give a little bit of an idea of what this kind of material looks like, I have here a hydrogel, a superabsorbent cylindrical sample in which we mixed a little bit of carbon to make it look black. We move it from a solution of high salt concentration to one with low salt concentration. And what happens is that it starts swelling. And the swelling that we see gives rise to what is known as the cauliflower effect. So surface instabilities develop because the outer layer swells first and the inner layers swell later. And what we see here now is a movement of ions going out of the gel at the same time as water is going in. Now, the amount of water that's going in is infinitely more than the amount of ions and results in swelling of the material. Now, as time goes on, the surface instabilities turn into a saddle shape of the cylindrical gel. And we see here the concave side of the gel being downwardly oriented in the plane of the image, and perpendicular to the plane of the image, we have a concave surface pointing up. So this saddle shape progressively reduces as the core of the gel is continuing to swell itself, so that the contrast between the outer layer being swollen and the inner layer unswollen becomes less and less. And progressively, the cylinder recovers its original geometry, which is strictly symmetric, axisymmetric, and regular in shape. And it recovers this cylindrical shape completely, showing that the material is strictly homogeneous. So the amount of swelling everywhere is typically the same. Only the symmetry breaking occurs because of the surface instability. Now, we should think that 90% of the biology, and therefore also 90% of the medicine, happens intracellularly. So all developments relating to medicines for instance, COVID-19 or cardiovascular disease or cancer or Alzheimer or whatever be the disease, should act inside the cell. inside the cell, we have a highly osmotic environment of very low stiffness. And this environment is very favorable to bring the behavior of a single molecule like DNA into expression on the microscopic scale. Now, the disappointing thing about this, the positive thing is that this area is a porous medium. The negative thing about it is that the present day poroelastic, poromechanical models are not suitable to describe this. Now, what happens inside is that we have a macromolecular network, which in a cell would be the cytoskeleton, and inside the gel is a set of polymeric macromolecules which are cross-linked. And both of them have a negatively charged nature, so that the macromolecules attract positive ions. By the way, we can draw a complete analogy with clay in geomechanics, where also there we find clay platelets which are negatively charged with positive ions around it. Now, these positive ions bind many times their own volume of water around them, causing to have thousands of molecules surrounding this macromolecule, which you see here in dark blue. Now, what we are going to assume, and we can reasonably do this for very deformable gels, is that ion diffusion coefficients are much larger than pressure diffusion coefficients. So ions can move much more quickly than water. And so we can assume that the ions are immediately in equilibrium with their outer solution, and as opposed to that, water is not. In other ways, another way to put it for those who are at home with poromechanics is that we assume the ion phase to be drained and the water phase to be undrained or partially drained. So what we come up with is the classical equations of finite swelling of a porous medium, fluid-solid mixture, just like described in the original paper from Maurice Biot in 1972. We have as first equation on top, we have the conservation of momentum. Second equation is conservation of mass. And third equation is Darcy's law relating flux to gradient in chemical potential. Now, if we put these equations into standard finite element codes, such as Abacus and others, we are very disappointed as soon as we go to very low stiffnesses. If we are in gigapascal stiffness, no issue. Even megapascal stiffness, which is typically cartilage, there is no issue. But once we go down 150 kilopascal, still we manage. 55 kilopascal, we fail for 50% of the time, and 15 kilopascal, which is the real stiffness we want to deal with, we find a failure all over. And the reason for this is local mass balance violation. Local mass balance violation is in fact pretty easy to understand if we think of a one-dimensional finite element model. For a confined compression of a sample, we find a linear variation of pressure, typically linear variation of pressure within an element or quadratic or whatever. But as an example, we will take a linear variation of pressure. We have a non-differentiability of this curve at the interface of the one element to the next. And the consequence is that if we calculate from Darcy's law the flow is discontinuous across the element boundaries. Now, this discontinuity across element boundaries basically means that there is more fluid arriving from one element than going into the next, which physically is an impossible situation. On average, this error will be reduced to 0 by means of the weak formulation, but still locally we have a violation of mass balance. So what we are going to do is develop a finite element in 2D and in 3D, which is able to comply with mass balance based on the intrinsic shape of the shape functions. And that you see on the right-hand side here. You see a quadrilateral element with 4 nodes, 4 displacements, and across each edge we have the flow as a degree of freedom, the flux through each of these edges, and this will allow us to force one flow from one element to be equal exactly to the flow on the next element. And the consequence is that this discontinuity across the boundary of elements will not be there anymore. So how do? We take the 3 initial equations, we turn them in a weak formulation, and we have a stiffness matrix coupled to degrees of freedom, and the right-hand side corresponding to these degrees of freedom. These degrees of freedom are displacement, flux, and chemical potential. And as an example, we take here a triangular element with 3 edges and therefore 3 fluxes and 3 displacements. And in the center, we also have a chemical potential. So we are going now to force this flux to be equal, coming out of that element equal to the corresponding flux going into the next element. And this we do by means of a Lagrange multiplier lambda 3, which enforces Q3 star to be equal to Q3. Now we will introduce this Lagrange multiplier into our system of equations, just as it is done classically in fluid mechanics, and we are left with an even larger system of equations involving displacement, flux, chemical potential, and Lagrange multipliers, which can be physically interpreted as the chemical potential along those boundaries. Now, what we can do is, on an element-to-element basis, we can eliminate the Q and the mu, so that we are left only with the displacement and the Lagrange multipliers, so that the size of the system of equations is comparable to the classical UP formulation, which all people in poromechanics know. Only in this set of equations, automatically, we fulfill local mass balance. And the result is that we have a very versatile piece of software here, Tetrahedral Elements in 3D, which describe very large deformations of a random volume, allowing to do simulations of what is happening within a diaper. And in fact, here another example is a ring which is attached to a surface on the top of the ring, and we bring it into contact with a concentration of lower concentration, and what happens is that the ring starts swelling and exhibits surface instability. And this kind of computation requires a very robust system which is able to cope with very low stiffnesses. So what we find is that even at 15 kilopascal, we are able to have a converging solution, which was not possible with the regular finite element formulations that we know from the commercial market. Now, we can do many computations now, analyzing the surface instability, and we find that if we plot our different computations as a function of swelling propensity and stiffness, we find that on one side the model is unstable, and the other side it is stable. And experiments published in Soft Matter by the group of Hayward in 2008 show a very similar picture. giving confidence that this simulation has something to do with the reality. And now I'm coming back to this original simulation experiment that I showed you using a cylinder, and we take a cylinder, cylindrical geometry using hexagonal elements and hexahedral elements, and we change a boundary condition from high salt concentration to low salt concentration. Note here that the geometry is strictly axisymmetric, and also the boundary condition is strictly axisymmetric. And we are going to simulate now the swelling, and we see that spontaneously here, just like in the video, there is a surface instability developing, although this is not really similar to the video, but at least we have some surface instability coming up. And the reason why this surface instability comes up, we can analyze it now looking inside the results of the finite element simulation, and we find that along the surface we have a strong compressive force developing, which means that the outer surface comes into compressive stress, and this compressive stress leads to buckling. Now, we are not only happy with only swelling, as for gels, the gels inside the diaper, we need also fracture. So fracture in hydrogels is a complex thing, and we are going to try to simulate this using XFEM coupled to large deformations. Now, before I start on this, I will start in experiment. We have a slit here in a hydrogel. The hydrogel is mounted in a tensile loading bench, and these two jaws are separating from one another so that this crack can grow. And this is a video, and the nice thing about a video with a gel is that the material is to some extent transparent. So you see it growing, and what is interesting to note here is that the crack is not expanding in a continuous fashion, but more into a stepwise fashion. And you see it also on the surface of the gel afterwards, is that there are typically teeth developing, and you can see it even better here on this other slide, where you see many teeth one after the other. Now, we have done not one experiment, but dozens of experiments, and we've compared the time of pause between the different staccato progressions and the distance carried during one progression, so the length of the teeth, and that compared to the stiffness of the gel. And here, so we plot stiffness of the gel versus distance traveled during one progression, that's the length of a tooth, and stiffness versus time of pause. And we see the time of pause is inversely related to the stiffness, while the distance traveled is increasing with increasing stiffness. This is what we find experimentally. Now, the interesting thing about this experiment is that we can reasonably assume that on the scale that we are looking, which is in millimeters, the hydrogel should definitely be a homogeneous material and isotropic. So it's not so that local heterogeneities can easily explain this phenomenon. Now, what we do, we use XFEM, and XFEM basically is a trick to do crack propagation within elements without remeshing. So in order to avoid remeshing, what one does, one enriches the degrees of freedom in the nodes, and the enriched nodes are indicated here with black. And as the crack goes forward, we have more and more nodes being enriched in order to be allowed to describe the discontinuity of the crack going through the elements. Now, the way that is done in a regular element, we have a displacement which is described by a shape function times nodal values. Here we have also displacement described by a shape function and nodal values, only we enrich it with a discontinuous shape function, which is this h times nu, and allows to describe a discontinuity in the displacement. Only what we do for a porous material, we also include a discontinuous shape function for the pressure. The pressure also has an enrichment which allows to have a pressure in the medium different left than right. And in order to be able to describe fluid inside the crack and the pressure of the fluid inside the crack, we introduce a third pressure along the same discontinuity, describing the pressure inside the crack. So we have three pressures, one left, one middle, one right. Now, this is an example of a calculation, which this time is not from biomechanics, but from geomechanics. We are simulating here a initial crack, small cracks, with around it a number of faults which were present already before we started the hydraulic fracturing, and we are going to pressurize these three cracks in order to propagate the cracks along the medium. There is no swelling until now in this simulation. So we see here how there is fluid accumulating inside the crack, and also at some point, as the crack propagates and reaches one of the faults, there is a communication of fluid between the new developed crack and the existing fault. And then at some point, the crack, continues to propagate and continues to propagate even beyond the fault which is present. So we can simulate cracks which merge together, which bifurcate, which initiate. All of this is possible using this analysis. In 2D, this works fine. 3D, we are working on it. This is a result in 3D, but I will not go into those details. I will come back now to the simulation of the hydrogel. We have a hydrogel with a slit here, and we want to simulate this crack propagation inside the hydrogel using this model, where along the crack we have three chemical potentials or pressures inside the crack, left of the crack, right of the crack. And what we get then is a opening of the crack in finite deformation. All of these simulations are done in finite deformation and progressively propagated. Now, what we find here is that, unlike what we expected, there is a stepwise progression of the crack. And you see here very clearly that the steps coming in, if we look at displacement versus time. And what is interesting is to see that this stepwise progression does not depend on the size of the time step. The time step can be taken longer or shorter. Whatever you take, you continue having these stepwise progressions. And if we plot now the propagation length across one of the steps versus shear modulus, you find that there is a positive relationship between one and the other, which is consistent with the experiment I just showed you before. And same thing is true for the pause time. There we have an inverse relationship between pause time and shear modulus, and qualitatively this corresponds to what we have been measuring in the experiment. Now the question is, why is it staccato? The crack is shown here and propagates to the right. Now, in order to propagate to the right, what we need is, in any material, we need a triaxial tensile state ahead of the crack, causing this crack to propagate. Now, suppose it is a porous medium, and in this case, we have a very deformable porous medium, so we can assume the solid and the fluid to be incompressible. What happens is that the pressure comes into under pressure around this point ahead of the crack. Now, this under pressure results in fluid flow going towards this under pressure area. And this fluid flow is going to cause this negative pressure to turn into an effective stress. Progressively, it will go into the effective stress, and the effective stress will turn into a triaxial tensile stress around this area. And after a while, so as the fluid flow has been able to flow in, we have a tensile effective stress, which causes the crack to propagate. Now, we can show that this is the case in our simulation by analyzing the relationship between propagation distance, pause time, and pressure diffusion coefficient. Propagation distance squared divided by pause time is in the same order of magnitude as the pressure diffusion coefficient given by the hydraulic permeability times the stiffness. And this gives us a hint that this stepwise progression may be associated with a consolidation phenomenon. So mixed hybrid finite element method has added value compared to UP formulation in poromechanics, particularly for very large deformations. At low stiffness and high swelling propensity, gels exhibit surface instability. There is evidence of staccato crack propagation in homogeneous gels, and enhanced local pressure and extended finite element method together is able to predict the staccato propagation of cracks in gels. Multiple cracks, merging of cracks, and bifurcation of cracks are within reach of enhanced local pressure, extended finite element method. So I want to thank the many people who have contributed during the years to this research. And I would like also to thank the many companies who have contributed to this research as well. So I thank you very much, and this paper is open for discussion.
Thank you for a very nice presentation. Are there any questions from the audience? Please. I do not see at the moment anybody. Maybe then I start with a question.
Okay.
Jacques, you are presenting mixed hybrid finite elements for swelling simulations and enhanced local pressure extended finite elements for hydraulic fracturing. Is there a benefit to combine both methods into one for fracture propagation in swelling media?
Thank you, Professor Van Kampen, for this beautiful question. There is a very strong reason, in fact, to combine mixed hybrid finite elements with XFEM. And why is that? The reason is the following, is that the amount of local mass balance violation that occurs typically becomes very large on places where there is concentration of stress and strain. That has been shown by many computations in fluid mechanics in the past. And now the situation of a crack is typically a situation where the whole stability of the whole structure depends on what happens around a very small area of the structure. And that makes the calculation extremely difficult, because around this singularity, we have major problems evaluating the stress and the fluid flow. Now, at this crack tip, I expect to have major problems with local mass balance violation. And so there is even more reason to do this mixed hybrid finite element modeling for crack propagation than without crack propagation. And in fact, I have to admit that the crack propagation that I showed you is not going down to 15 kilopascal. We cannot do it. So if we want to really do the cracking simulation for very low stiffnesses, I think that mixed hybrid finite element or even more advanced methods such as isogeometric analysis is mandatory. And so this is a very important line to go for the future.
All right, thank you. Any more? Yes. Merlin Aragon. I cannot see the complete name. Merlin Aragon Etzold.
Yeah,
Go
hi.
ahead.
I hope you, I can't switch on my camera, but I hope you can hear me. That was really a nice talk, very interesting. Thank you. I have a number of questions, but the first one I would like to ask is, when you go back to your last slide where you explained the stepwise propagation of the crack, just for my clarification, so you have this region of under pressure at the tip, which swells and eventually pops, if I may say so. And this under pressure is caused due to the vertical strain imposed by the mode 1 crack. Is that correct? I didn't catch that properly.
Thank you very much for the compliments. Indeed, let's go back to the slides we are talking about. The under pressure develops indeed because of the traction applied by the tensile testing bench onto the gel. And we can see that there under pressure develops, at least during the simulation, we can see that under pressure develops. And this is necessarily the case because fluid and solid behave less like an incompressible material. And the only way to respond for the material is to go into negative pressure. And the result is that because this happens very locally, the fluid flow is going to stream towards this from areas where it is not so. And the result is that very locally you have a triaxial tensile strain on the macromolecular network of the gel. And so there the gel macromolecular network fails. After a while, each time waiting a time, and then propagation occurs, and then again under pressure occurs a little further, and the same procedure is happening all over again. This is the only explanation that we have for this staccato propagation. It is not so that all staccato propagation should be explained like this. I can imagine very well that in many geotechnical situations, there are local inhomogeneities which cause stepwise progression of the crack, which have nothing to do with this phenomenon. So we're not claiming that this is true also in very stiff media.
Okay, thank you.
Okay, one more question. I don't know how strict I have to keep time, but maybe room for one more question. I don't see anyone. Well, then I put myself one more. You are presenting diapers as an area of application of combined swelling and fracture simulation. What is your opinion on hydraulic fracturing of shales as another potential important application area, as shales are swelling as well?
Thank you for the question. The shales is an area which has drawn a lot of interest from myself, but also from other people. And particularly, shales have been important for the extraction of gas. And it has the extraction of gas shales from the US underground and Canadian underground has in fact transformed the whole energy market in the world, because it turned out that this hydraulic fracture was extremely successful in enhancing the flow of gas out of a gas shale. And my colleague Bazant from Northwestern University has published repeatedly within the geotechnical journals that the only way to explain the high output of gas that is obtained from the gas shales everywhere in the US is to assume there is a very dense network of fractures all over inside the shale generated by the hydraulic fracturing. And his critique against XFEM is that when you do XFEM simulation on those shales, you find just one crack, and that's all. And he says, yes, but there should be thousands in order to explain the output of gas. Now, I think that what is missing within XFEM simulations and other simulations inside shale is the swelling propensity, because particularly once you apply hydraulic fracturing, one thinks one applies pressure inside a crack, and that is true, one applies pressure inside a crack, but one brings also a highly osmotic material into contact with fluid, which it has not seen for millions of years. For millions of years, there was no water down in 2 meters below the surface of the earth. And so suddenly you bring them into contact with water. This shale is going to tend to swell like crazy, and shale being brittle, it goes into pieces. And so I think the swelling propensity of shales is absolutely vital to understand hydraulic fracture of gas shales. And I think there is immense opportunities there to get much more realistic simulations of the phenomena happening within gas shales.
All right, thank you very much. I think in view of time, we have now to close this session. Jacques, thank you once again for a very nice presentation, and also those who contributed to the discussion, I want to thank. I close this session.
Thank you very much.